In this video, we'll discuss the idea of impulse and introduce you to momentum. So let's consider this problem. A crate starts with an initial velocity of 3 feet per second and is pulled down a slope, 30-degree slope, with a coefficient of friction of 0.3 by a force P, which is a function of t, and that equals P equals 20t. Let's find the velocity after 20 seconds. So we could, based on what we learned so far, we could look at the kinetics here. Here's my free body diagram. We know that this is 30 degrees here now. And we'll set this equal to the mass times acceleration, our inertial condition. So if I sum forces in the direction of our acceleration, we get P, which is 20 times t. Subtract off our force of friction is 0.3 times the normal force. Our normal force is a portion of this weight, which is 50 cosine 30. You can find that by summing forces in the direction perpendicular to our acceleration. If you can't spot that right now. But then finally, we also have a force due to weight pushing down this slope of 50 sine of 30 degrees. And all these things equal our mass, which is 50 pounds, divided by 32.2 times our acceleration. So in this relationship, we can find acceleration as a function of t. This, solving the above equation, simplifying the above equation, we get 12.88 t plus 7.734, or abouts there. Okay, so that would be our step one typically, solving a problem like this. Now we will need to do some kinetic work with a step two, and that might look like this. So we'll start with this differential equation. Then if we integrate both sides, we go from initial velocity of 3 feet per second to our final velocity v that we're looking for, and we integrate from 0 to 2 seconds our acceleration, which is the equation above, 12.88 t plus 7.73. Correcting that, then we can solve for v, and v turns out equals 44.2 feet per second. So that's all a review from past chapters. Now, what we could do though, however, is notice that our sum of forces equals, our sum of forces as a vector equals mass times acceleration as a vector, and this equals mass, if we consider mass constant, times the derivative of our velocity with respect to t. And we can solve this differential equation. So we can look at a situation where we have sum of we can integrate, separate variables and integrate. So we could do a sum of forces dt from t1 equals 0 to t2 equals 2. This then would equal mass times the integral of v1, which was equal to, v1 was equal to 3, and we're going to go to v2 and then dv. And solving this directly then. So we look at this, we end up with a situation where this equals mass times v2 minus mass times v1. We call these terms our linear momentum. our initial and final. V1 is our initial, V2 is our final linear momentum. These terms are in the same direction as V, and this equals this integral over here on the left, which we call the linear impulse. So linear impulse is a force times time. Essentially the area under a general force curve. In this case, our force equation is a linear equation in time 20t. So rearranging these terms, we can get something that looks like this. I wonder how this will look. Where the impulse is on the left with our initial momentum, and that equals our final momentum. Up here, I really probably should take out these numbers because we're actually solving this in a general sense right now. So this can then break down into three scalar equations. So our first then would be mass times the velocity in the x direction initially, plus the summation of the integral of our forces from t1 to t2 in the x direction equals mass times the velocity in the x direction 2. Similarly, we can get equations in the y and z direction, as shown here. And now, in one step, and here I've redrawn our free body diagram. So let's continue on here. This is our positive. Let's look at and let's say we call this the x direction. Let's look at mass times velocity in the x direction. 1 plus the sum of t1 to t2 of our force in the x direction dx equals our mass times velocity in the x direction final. So putting some numbers in here for these things, we've got 50 over 32.2 for the mass. Our initial velocity is 3 feet per second, plus we'll integrate this from 0 to 2 of our force, which is, so we got to take into account all our forces. First we have P, and then we subtract off minus our friction force as before, that the normal is 50 times the cosine of 30 degrees. And we add to this our weight component of 50 times the sine of 30 degrees dt. And then this is going to equal our mass of 50 over 32.2 times what we're looking for, our final velocity in the x direction 2. So we only have one unknown here. We can certainly solve that relationship for v of x equals, again, 44.2 feet per second. So here, let's try another problem. This is similar to problem 1514 in the 15th edition, Hibbler. We've got this train car that's moving along at, I think it's 0.75 meters per second. And center of gravity weight of 20 times 10 to the third kilograms, and then we have to multiply that by 9.81 is the weight of our car. So let's go ahead and figure this out. Velocity 1 plus our impulse. I'm just going to draw it as the integral f dt equals m2 v2. So m1 v1 is 20 times 10 to the third times 9.81 plus, we'll just put an I in here for this, equals 20 times 10 to the third times 9.81. And then our velocity 2, I guess I spent a lot of time writing this for nothing, is going to be 0 if this thing stops, if that brace stops it. So just simply get impulse equals, now let's keep in mind here that if this is our train car with weight, then the force to stop this is going to be in this direction. And if we're taking this as the positive direction, this really should be a negative here. So now I can say impulse equals this 20 times 10 to the third times 0.75 20 times 10 to the third times, we're missing our velocity term here, 0.75 meters per second. This should then equal something like 1.5 times 10 to the third Newton seconds. So it's interesting to note that it doesn't matter what our bounds of integration are here, that this impulse is going to be the same. No, the difference is that if this has a little bit of spring to it and it takes a second or two to stop the vehicle, the impulse is still going to be the same. And that's that.